Okay, so let us start our class now. So we'll quickly go through the topics we covered in the previous session, and then we will continue with week 11 today. We'll start week 11 today. Okay, week 11 is comparatively easier and less topics to cover also. Okay, fine. Okay, so in week 10, the previous session, what we saw was how to find the steepest ascent and steepest descent if you are given a surface, right? Or surface or any multivariable function, how to find the steepest ascent and steepest descent. What is steepest ascent and steepest descent? Direction in which something is increasing the fastest. Okay, fine. Increasing or decreasing. Okay. I'm audible to everyone, right?
Yes, ma'am.
Okay, fine. So what we saw was that to find the steepest ascent, you need the directional derivative to be positive and the maximum value it should have. And the direction in which it happens is the direction of the gradient here, right? The gradient function. Okay. And here, since u is a unit vector, you are considering the unit vector in the direction of the gradient function. Okay. And the steepest descent happens when you have the directional derivative to be negative in the mean, and also it should be the minimum value. Okay, and it happens in the direction opposite to the direction of the gradient function, gradient vector. Okay, and there is no change in the function when your directional derivative is 0 and u is orthogonal to your gradient of f. We saw how these directions came. That details we have discussed in the previous session. So just I saw that this example, you can have a better idea of how this is happening. See, you are having the surface plot of x squared plus y squared. Okay, so this is the surface plot of x squared plus y squared. Now, obviously, you see, take any point here, in what direction it is going to increase the maximum. You see, it is kind of, you see, like this, it is increasing, right? The maximum increase you can see in a given direction, it is very easy to see in this particular graph. And here they have considered the gradient plot of x squared plus y squared. So gradient plot means given a point, what is the gradient of that function at that point? That is what they are considering. For this x squared plus y squared, what is the gradient?
2x comma 2y.
2x comma 2y, right? So if you are taking some point, for example, if you are taking 1 comma 1, for example, then you know the gradient is simply 2 comma 2, right? So it is going to just increase in this direction only. 1 comma 1, the gradient function is in this direction, right? So any vector you take, the gradient function, it is going to increase along the same line, right? So here you see this direction here is representing the direction of the gradient. So the gradient vector points into the direction of the steepest ascent. That is what we know, right? So the steepest ascent, the fastest increase, you see. So that is nothing but the gradient. It is in the direction of the gradient function, right? We know the steepest ascent happens in the direction of the gradient function. It is very clear to see from this graph. Okay.
Ma'am, I have a doubt.
Yeah.
So, like, can we say that the steepest ascent is where the function is at its maximum as well?
No, 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 no. It is not like maximum. See, maximum or at these points, right? That is
Yes.
not what we are studying. See, where it is going to increase fastest. What is the fastest direction? Suppose you are considering a specific direction, how fast it is increasing in that specific direction. So, suppose you are considering at this point 1 comma 1, how far and which direction it will increase the fastest. If you want to say, then you look at the gradient of that particular point. So here, for example, I told you 1 comma 1. If you take, then it will be 2 comma 2. In the direction of 2 comma 2, it will increase the fastest.
Okay,
Okay.
so like it's not always the case that it will be the maximum at that point as well.
No, no.
Okay. And one more doubt, if we have, let's say, two values, minus 10 and minus 5, so minus 10 will be considered as the minimum, like steepest descent point.
Yeah, yeah.
Okay, okay, okay.
Okay, fine. Okay. So after this, we saw what are tangents for f of x comma y. Let f of x comma y be a function defined on a domain D in R2 containing some open ball around the point a comma b. Okay, so you are having some surface and you want to find what is the tangent for this function. Now this is a surface. F of x comma y means the graph of this is actually a surface, right? Surface in 3D, right? So you are having a surface in 3D and you want to consider a point a comma b in for this surface. So equation of tangent lines to this function f at the point a comma b in the direction of the unit vector u1 comma u2. So these are the equations we saw. So parametric equations and vector form, they are almost the same. And for symmetric equations, you know that for symmetric equations, we obtain it by taking each of these parametric equations by equating it to t, whatever we are getting, that we together write it and get the symmetric equations, right? So these are the three different forms of tangent equations. Mainly we are using the parametric equation or the vector form, right? Okay. And yeah, here you see that for x and y, the direction of we are considering here is in the unit vector u1 comma u2. So you are having u1 u2, and the z coordinate, you are having the image of this function value, so f of a comma b, right? So that is the z coordinate you are considering, right? In the surface, what are the points you are considering for this graph of the surface? X, y, and the third coordinate is nothing but f of x comma y. Okay, so for this, and what is the corresponding direction in which you get the line? So it is the direction of the directional derivative, particularly at that point. Okay, so this is what we see for parametric equation tangents for two variables only. And when it is for any n variable, so this is the general form you are having. So this is the equation of tangents. So from equation, remember when you are having, suppose say a function of three variables x, y, and z, then how do you write the parametric equation? Let us say it will be with some other variable, maybe w of t or some other u of t, okay, or some other function name, okay, f of t or whatever, okay. So depending on that problem, you should understand what is the last variable representing, okay. Don't always fix that the third z means just the third coordinate is z. So depending on how many variables you are using in that function, you have to understand what is z, okay, fine.
Oh, so ma'am, like what does it represent, the tangent plane in four variables?
See, as I told you in the here x, y, z, if you are considering x, y, and z, they are all different axes. Okay. And
Yes.
the fourth one is f of x comma y comma z. The fourth coordinate is f of x comma y comma z.
Yeah, but we cannot visualize it. So like, how do we
No,
even
no, we
like?
cannot visualize. Only up to 3 dimensions we can visualize. After that, we cannot visualize. Okay, that is why usually whatever things we are studying, we study up to R2 and R3, and then we give the general statement. Okay.
Yes. Okay.
Okay, fine. So, what is the condition under which the tangents exist? Suppose you have a function of n variables, okay, and you have a point A tilde in the domain D with some open ball around it, okay. By the way, some of you asked some reference for this equations of tangents and tangent plane. I have added it at the end of this document. Okay, you can refer to it if you want. Okay. Let f of x1, x2, xn be a function defined on a domain D in Rn. So now, when does the tangent exist at this point for this function? So for this, you want the, first of all, the gradient function should exist, and it also should be continuous on some open ball around this point. Then for every unit vector u, the directional derivative fu of a tilde exists and equals to the dot product of the gradient and the vector u. Okay, that means what? This is nothing but what? This is the directional derivative at the point A in the direction of u, right? So you see all the tangents at a point A tilde exist when del f exists and is continuous on some open ball. Okay, so when this condition is there, you know that You need this existence of this particular thing. That is why this condition is coming. Okay, so fu of a tilde exists when you have this condition, and if you fu of a tilde exists, then you can easily write what is the equation of the tangent. Okay, fine. Now, what is the equation of tangent plane? So this is the equation of tangent plane. It is given. So this is much easier to remember, because in the case of one dimension, the equation is very simple like this. So the same you are having in n dimension, z equal to f of a tilde plus del of f of a tilde into, here it is not into, here it is dot product. Remember, it is dot product here, not into, it is dot product. Del f of a tilde dot product with x tilde minus a tilde. Okay, so this is for finding the equation of the tangent plane. Okay, and we saw that this tangent planes are nothing but the linear approximation. What is happening? They are nothing but the linear approximation. Suppose you are having some curve. I am not very good in drawing this 3D structures and all. Anyway, some 3D structure. This is some 3D structure. Imagine. Okay, so some 3D structure like this is there. Okay, so suppose you are considering this particular point. Okay, and what does this linear approximation means? At near this point, okay, near this point, what can be an approximation for this function f near this point? And it should be a linear function. Okay, so if you are considering a line, then that line is a linear structure. And also if you are considering a plane passing through this point, and also it contains the tangent plane, suppose, let's say, so then that is the linear approximation for this point, for this function. Okay, so let f of x tilde be a function defined on a domain in Rn containing an open ball around the a tilde. So this is your a tilde. Okay, suppose del f exists and is continuous on open ball. So only if you have this, then you know the tangent exists at. So you know that tangent exists from this condition. So since now tangent exists, then you know how to find the linear approximation. Linear approximation is exactly the tangent plane at this point a tilde. Okay, linear approximation is the tangent plane at this point a tilde. Okay.
Excuse me, ma'am.
Yeah.
Is it from week 10?
Yes.
Okay, ma'am. Actually, I joined a bit late, so that's why.
Okay.
Okay. Thank you, ma'am. Carry on.
Yeah. Okay. Fine. So after this, as I told you in the previous session, there were three important topics which we covered in the previous session. So the first one was the steepest ascent and descent, and then the tangent concept, and then the local extrema and global extrema. So here, what are local extrema for multivariable functions? Okay, so local extrema, for local extrema, you are just considering some open ball B containing a tilde. Remember, when you are talking about local extrema, you are considering some open ball B containing a tilde under which this condition is satisfied. Okay, so for maximum, all the points within this ball should have value less than the value at the point A. And for minimum, all the points should have values greater than this point, right, inside this ball. So such points are called local extremum. Okay, so how do you find at this local extremum? Okay, at the point of local extremum, you know that the gradient function is 0. Just like in the case of 2D, in the point of local extremums, the derivative is 0. So suppose in the 2D case, it is very easy to see, right? For example, if you are having a curve like this, then you know that here you can see a local minimum. So here you see local maximum, local minimum, local maximum, and all at all these places you see the derivative is 0. Right? So it means here the concept similar to derivative, here you have the gradient. So you are considering the gradient to be 0 for the local extrema points. Okay, fine. So now what are critical points? A point a tilde is called a critical point of a function f of x tilde if either del f of a tilde does not exist, or del f of a tilde exists and del f of a tilde equal to 0. So either this or this. Okay, in both the cases, it is called a critical point. Okay, even if it does not exist or if it exists and equal to 0, in both these cases, you call that point to be a critical point. Okay, fine. Okay. So what are so you see critical points can happen somewhere where you have discontinuities or where you have, so for example, whatever happens the 2D, the same thing you have to remember here also. So whenever you have a sharp edge like this, you will have a critical point, or whenever there is a discontinuity also. Okay, so in such places you may have critical points. Okay, and what are saddle points? Every local extrema is a critical point. Saddle points can be better understood from 3D rather than from 2D, because what are saddle points, as I told you in the previous session. So saddle, you remember saddle of a horse, so where the rider sits, that's a saddle. So for the saddle, when you look it from the side, the structure, it will have a minimum value at that particular point. The same structure, if you are looking from the front, it will look like this. So it is something like this from the side. So, and when you are looking it from the front, so it will actually look like this. So at that same point, you will have a local maximum. In from one direction, it is like this minimum, and the other it is maximum. So it is neither a minimum nor a maximum value. So such points are called saddle points. Okay, so every local extremum is a critical point, but not all critical points are local extrema. So such points are called saddle points. So a saddle point is a critical point such that del f of a tilde exists and del f of a tilde equal to 0, but a tilde is not a local extremum. Okay, you are
Ma'am, basically, it's a critical point where there is no minima and no maxima, but it's a
exactly.
critical point, so it's a saddle
Yes.
point.
Yeah. Okay. So such points are called saddle points. Okay. So for example, in the case you see in the 2D case, for example, the usual example we consider is the graph of x cube, which is like this, right? Not exactly like this. So here you see that the derivative of this function at 0, f dash of this function at 0. See, you see that here it is the derivative is 0 only, right? So here you know that at this point the derivative is 0. So you have a tangent along the x-axis actually, but so it is a critical point. But anyway, it is not a local minimum or local maximum, because you see in the right side all the points are greater and in the left side all the points are lesser. So you cannot take any interval where all other points are greater or lesser. So here this is a saddle point in the case of 2. So here in the 3D case, it is something like I mentioned before. Okay, fine. So anyway, remember they are saddle points, but they are not local extrema. Okay, and the next concept we are having is absolute or global extrema. So for as I told you, the comparison between local and absolute is that for local, remember you are considering only the values in an open ball containing A. Okay, but for global, you are considering the entire domain D. For global, you should consider the entire domain D. So here for all x in D, this condition is for all x in D. Okay, so this is the main difference between global and local extrema values. Okay, so you see for maximum all other values should be less than this value of this function at the point for the domain itself, and for minimum all other values should be greater than the value of the function at a tilde. So here it is a tilde and x tilde. Okay, and when does the what is the condition under which the absolute maxima exist? So if the domain D is closed and bounded and f is continuous on D, then the global maximum and minimum must exist. Okay, your domain should be if closed, bounded, and f is continuous on D, then the global maximum and minimum should exist. Okay, fine. Now, what are the steps involved in finding the absolute extremum? First point is that you have to find the critical points that lie in the region D. How do you find the critical points? What is the step to find the critical point? You find what is the gradient function, equate it to 0, solve for it, and the points you get are the critical points, right? And whatever points you are getting here, you determine the value of the function at these points, right? And then you consider the boundary values, and at the boundary values, what are the critical values and what are the values of the function you calculate. For example, in the case of the square, which we consider the square example, right? What we did first, you did this first step, and then here for this particular case you considered, I guess it was 1. So you took x is equal to 1 and the value of y varying between 0 to 1. For this what happens, and for this what happens, like this individual cases of boundaries you consider. Okay, so now whatever points you have found from step 1 and step 2, at all these points you find the function values, compare them. The largest and smallest value are going to give you the absolute minimum and absolute maximum. Okay, note that there can be multiple absolute minima or maxima. Okay, for example, the same, suppose let's say f of x comma y is equal to 10. For some point you are getting, for some x naught y naught you are getting 10. You may get some other point f1 x1 at 10. So if 10 is the maximum value, it is possible that both x naught y naught and x1 y1 at both these points you may have a maximum value, absolute maximum value. Okay, fine. Hereby, please remember, multiple absolute minima and maxima I mean by for these points, not for these values. Okay, the maximum value is the same. I'm saying can occur, can maybe I'll write can occur. Multiple absolute minima or maxima can occur in several places. Okay, can occur in several points. Okay, fine. Okay, so with this, we will now start with week 11 topics. So here we are starting with week 11 topics. So we have seen only the first derivative properties in up to week 10. So now in week 11, we are going to look at higher order partial derivatives. So they are quite simple. If you know what are partial derivatives of first order, second order, and other higher orders are pretty much the same. Okay, so let f of x comma y be a function defined on a domain D in R2. Then the second order partial derivatives of f are the partial derivatives of the partial derivatives. So it means now your function here, for example, what is this? The second order partial derivative with respect to x. Okay, so here the function is fx. Okay, and you are doing f dash of fx with respect to x. Okay, so you mean here what, so for example, suppose you are having f of x comma y is equal to, let's say, x squared plus y squared. Now what is your fx here? What is your fx?
2x.
2x, right? So now you have to consider this as a function and find the derivative again with respect to x, then that will give you
2.
Okay, now suppose you are considering this as a function of x and y, then what will happen to the derivative of this function with respect to y?
Again, xy 0.
0, right? Because here you don't have the variable y, so
No
x
y
is
in
considered as
fx,
a
so
constant.
fxy is 0.
Yeah, so you are having fxy is 0. Okay, so you I guess these terminologies are familiar for you. I don't have to explain these terminologies. It's clear for everyone, right, what we are doing here? So either this terminology or this terminology. Okay, whichever is convenient, you can follow. For this one, please understand it clearly. What is the first thing you are doing here? Already you are having dou f by dou x. Okay, and for this, you are performing what is dou by dou y of this function. Okay, so since y is there, you first think that you are finding the first y, and then with respect to x. Anyway, it is not going to matter. You will see that both of this expression are same for some specific functions. But anyway, it is good to know that it means that first you are finding the partial derivative of f with respect to x, and then you are again considering the derivative of this function, new function now, with respect to y. And here you are considering the partial derivative of y first, and then you are considering the derivative with respect to x. Okay.
Teacher,
So for, yeah,
but ma'am, this cannot be same because in some cases,
I
it
told you in specific cases, yes. In there are few cases where it is not true. Yeah.
correct.
Okay, fine. So let us start from some very basic examples. So f of x comma y equal to x plus y. So what is the partial derivative with respect to x?
1.
1. And with respect to xx, so you are again
0.
differentiating with respect to x, it will become 0. Okay. Now, what is fy?
1.
1. And what is fyy?
0.
0. And what is, maybe I'll write separately first before we look at the theorem. What is fxy?
0.
This, yeah, again 0. And what is fyx?
0 again.
0 again. All right. Okay. And now let's look at the next one. What is fx for this function?
Y cos xy.
Y cos of xy. Okay. And what is fy?
X cos of xy.
Right. And what is fxx?
0.
Please be careful.
Sorry,
minus y
that's
square
minus y cos
minus y
xy.
square sin xy.
Minus y square
Sin
sine
xy.
of xy.
xy.
Okay.
Yes.
And what is fyy?
Minus x square sine of xy.
Sine of xy. All right. And what is f of xy? So this is the function now. What is the derivative of this function with respect to y? So now if it is with respect to y, you have to consider this in the form of u and v. So this is your u and this is your v. You have to treat it as uv for f of x comma y. Derivative of this with respect to y you are considering. So what is that you will get? So first u into v dash. So you have minus x times of x
Y
into y
sin-
times of sine
Sin of
xy.
xy.
And then what happens? And then you are getting,
Plus cos
Plus
xy.
cos xy.
yeah. And then you are getting plus cos xy. And what about f yx? Again, it is similar, right? You have to use the same UV technique. Minus
Minus xy sine xy
plus,
plus cos xy.
yeah. Okay, fine. Now for this function, what is your fx? Here you see, if you are considering fx, then here
Minus
it
e
is
to the
just a
power 2y
constant.
sin x.
Yeah, so you can consider this as a constant, and this is simply minus sin x. Okay, and what is fy?
2
e
e to the power 2y cos x.
Okay, and what is fxx?
Minus e to the power 2y cos x.
And fyy?
4 e to the power 2y cos x.
Right? And what is fxy?
minus 2 e to the power
Minus
2y.
2 e to the
Now
power
you have to
2y sin
consider
x.
UV method, right? So first, with respect to y, if you are still not
No.
UV, only you
Yeah.
have this other values constant. Yeah, yeah. So minus 2 times of e to the power 2y sin
Cos
x,
x. Sin x. Yeah.
and then fy with respect to x. Now, So this is now a constant. So you keep it as it is. And then what is the derivative of cos x?
Minus sin x.
Okay, that's all. What about this function here? What is your fx? Yeah,
3 times of e to the power 3x minus 1. 3x minus 5.
yeah. And what is fy?
Same, e to the power 3x minus 1.
Are you sure? It is minus e power 3x minus y, right?
Like y minus?
And what is fx, xx?
Okay, ma'am, I didn't get it. Why did you put
3
minus e?
Because here what you did, here you are using chain rule actually, right? What is the derivative of e power, e power f of x
Okay.
comma y you are having, okay?
Yeah.
Now what is the derivative of e power something? It is the same, right?
Yes.
So you will first write e power f of x comma y. Now here using chain rule, then for this function you will find the derivative, right? So what is the derivative of this? You will write with respect to x. So this is for with respect to x, and with respect to y, fy of x comma y e power f of x comma y. Since here f is there, maybe I use g. Okay. So g with respect to y x comma y. So if 3x minus y is your g of x comma y is 3x minus y. So what is the derivative with respect to y?
Minus 1.
Got it?
Okay, yes, ma'am.
Okay. Sorry for writing in this way. So here, let's say g of x comma y. Then here it is gx, and here also it is gy. Okay, fine. Okay, so what is fxx?
9e to the power 3x minus y.
And what is fxy? Yy?
E to the power 3x
E
minus
to the
y.
power 3x minus y.
Okay, and what is fxy?
Minus 3
Y minus 3e to the power
e to the
3x
power
minus y.
And what is yx?
Minus
same.
3
Minus 3
e
to the power 3x minus.
minus 1.
Okay. So for this kind of questions, mainly you see that only you either multiply 3 or minus 1 repeatedly. Okay. So when we go to higher order partial derivatives, remind me to come back to this problem. Okay. Some specific type of questions can be asked from this kind of problem. So I will tell it when you are looking at higher orders, maybe 3 or more. Okay. So before that, let f of x comma y be a function defined on a domain D in R2, containing a point A tilde and an open ball around it. So if the second order mixed partial derivatives fxy and fyx are continuous in an open ball around A tilde, then you have this equality. So far we see that all these functions are very smooth. They are very continuous functions. They don't have any discontinuities very obviously. So here in all these cases you see that this coincides. fxy and fyx, the partial derivatives, mixed partial derivatives, they coincide. Okay, but some cases it is possible that the partial derivatives need not be continuous. In that case they will not be equal. Okay, so Clairaut's theorem is this condition is valid only when you have the continuity of the mixed partial derivatives in some open ball. Okay, so this is Clairaut's theorem. So here is an example which says that without the condition mentioned above in Clairaut's theorem, the condition that fxy and fyx need not be equal. Okay. So now let us look at this condition. Now what is the fx of 0 comma 0? What is the derivative of this function at the point 0 comma 0? Remember, whenever we have some kind of function like this, where you have a step function like not step function, you have a piecewise function like this. I have told you it is recommended that you use the limit technique to find the partial derivatives, right? So
Yes.
let us use
Yes,
the
ma'am.
limit technique to find the partial derivative. So limit h goes to 0. Here, what is that we should write with respect to x means? What is that we should write? Can you tell? Do you remember?
F of
fx of
0 plus h e I.
See,
Yeah,
okay,
h
HEI you can E1 actually, which is
yeah
actually straight away 0 plus h comma
h
0, right?
0. Yeah,
Yeah, and then minus f of at which
0
this
comma
point
0
is 0 comma 0. The whole divided by
h
h. And what is now f of h comma 0? For
0
h comma 0, you have to see here. If
0
one value is 0, you see the term becomes 0. So here it is limit h going to 0. F of h comma 0 is 0 and f of 0 comma 0 is also 0. So this value becomes 0. Okay. And what is the partial derivative at with respect to y? It is also going to be 0 comma h minus f of 0 comma 0. Again, you are going to get the same. So here in this case, you are going to get 0 comma h minus f of 0 0 by h. Again, you know that this is 0. So it is 0. Okay, so this is a partial derivative at the point 0 comma 0. What about the partial derivative of this function at non-zero values? So now let x comma y not equal to 0 comma 0. It is not the origin. Okay, now for such points, what is the partial derivative? For this point, you don't have to use the limit technique. You can use straight away the partial derivative formula, you know. So here it is in now u by v formula, right? If it is in the u by v form, what is the formula you need to do?
v u dash minus u v dash
v dash by v
By
square.
v square.
Okay, let us use this. So here you see in the denominator, you will have
x
x square
square
plus y
plus y
square
square the
the
whole
whole
square,
square. Okay, and the numerator you have
x
v.
square plus y square.
Okay, so
Very
before
easy.
doing this, it is better if we simplify this so that it is easier for calculation. The numerator,
X
what
cube
is the
y
numerator?
minus x cube y minus xy cube.
Okay, so let us use this numerator now. Now, what is the derivative of this with respect to x?
3x square y minus y cube.
Minus
Y cube.
just y cube, yeah, minus y cube. And then minus u times of
X cube y minus xy cube.
your v dash. What is your v
2xy.
dash?
2x. 2x.
2x, right? So let us simplify this and see what we are getting. So you get 3x power 4 y plus 3x square y cube minus x square y cube minus y power 5, and here for this minus 2x power 4y
Plus
minus into minus plus
plus 2x
x
square y cube.
and the whole divided by x square plus y square the whole square. Okay, now let us combine the terms which have common coefficients. So here x power 4y and minus 2x power 4y. So if these two terms are combined, what will you get?
X power 4y. X power 4y.
X power 4y and x squared y cube and this three terms have the same coefficient. So what is it you will get? 3 minus
4.
1 plus 2
4x square plus 4x square y cube.
and the remaining term is minus y power 5. The whole divided by x squared plus y square the whole square. Okay, this is a partial derivative with respect to x. Now what is a partial derivative with respect to y? We have to do the similar steps. Okay, so you will have denominator x squared plus y squared the whole squared is going to be the same. So your u is, if I remember correctly, it is x cube y minus xy cube, right? That is your u, right? Yeah.
Yeah, x cube y minus. xy.
Now, with respect to y, if we are using the same formula, so x
You
squared
get
y
x square
squared
y square into x cube minus 2xy square. Sorry, 3xy square. 3, sorry, ma'am. 3xy square
mm, minus
minus
mm,
x cube y minus xy cube into 2y.
right. Now this is
Yeah.
equal to x bar 5. Do we have enough space to complete? Yeah, I'll write in the next line only. Okay. So here you have x bar 5 plus x
Minus
cube
3.
y square minus 3 x cube y square minus 3 xy power 4,
xy power 4
and then minus
minus
2 x cube
x cube y
y
square
square
plus 2xy power 4 x square y square the whole square.
right. Now let us club the terms which are common. So x cube y square, these two, and here this another one, and then
1
you have these terms are also common. So these two. So you have to club them together. All right. So if you are clubbing them together, you have x bar 5
perfect minus 4
minus 2 minus 2. So
minus
minus
4
4 x
x
cube
cube y
y
square
square, and then minus
minus
xy
1
power 4.
xy power 4.
The whole divided by x squared plus y squared whole. See, again you are having both the partial derivatives are becoming again piecewise functions, right? So when xy not equal to 0, you are having some function, and at 0 it is some other function. Okay, and these functions fx and fy, they are not continuous at the point 0 comma 0. Okay, you have to verify it yourself at the point 0 comma 0. If you are finding the limit of this function at 0 comma 0, it will not be equal to 0 comma 0. Okay, you can verify that. So in this case, you see that your partial derivatives, if you are finding your fxy and fyx, I guess that step is at the point 0 comma 0, it is given. Maybe I'll write it in a different color. So let's write what is your dou square f by dou x dou y at the point 0 comma 0. Remember again, since we are considering at the point 0 comma 0, we are using the limit formula rather than the straightforward formula. So limit h goes to 0. So now what is the function we need to write here? Can you tell correctly? What is
Fy.
the, yeah?
Fy, right?
Yeah, fy. And then which point we are considering here with respect
X.
to x? So
X,
it means h
H
comma 0.
comma 0.
The whole divided by yeah. Okay, and now limit h goes to 0. Now what is fy of h comma 0? This is your fy function. Okay, for the points x comma y not equal to 0, you have to look here. For fy of h comma 0, what is it you will get? X value is h and y value is 0. So what will you get?
H power 5 by H power 4.
And then you have another divided by h.
H.
So this will become limit h going to 0,
1
h by h, which is
1
1. Okay. Now let us look at what is dou f by dou y dou x. Dou f squared by dou y dou x at the point again 0 0. Now can you again tell what is the limit formula here? For which
Fx
function? Yeah,
0,
fx.
0 comma h
Yeah.
minus fx of 0 comma 0 by h.
Now what is here? Now you have to consider in this place, you have to consider x is equal to 0, y is equal to h. So what is that you will get?
Minus h power 5
Hmm.
by h power 4 by h.
So which is
Minus 1.
minus 1. Okay. So now do you So are the partial derivatives same at the point 0, 0? The mixed partial derivatives, are they same?
No.
No. So it means why this has happened. You look at the Clairaut's theorem. So in the Clairaut's theorem, only when you have the continuity at the point A tilde, then only you have this equality of the mixed partial derivatives. Here, this functions fx and fy, they are not continuous at the point 0, 0. That is why we are having this kind of problem. So whenever you are having particularly this this
0,
kind of
0.
piecewise functions, okay, piecewise functions, particularly there are functions which are not piecewise, still we have to be careful. So this is kind of a hint that you should be careful at these points. Okay, fine.
Ma'am, can
Yeah.
you brief what is the condition for checking the continuity?
For checking the continuity, you have, what is that you need to do? You have to find the limit of this function.
Limit has to equal to the value in that term.
Limit x comma y going to 0, 0 of f of x comma. Here actually you have to look at fx. Okay, x comma y you have to see. Okay, if this is not equal to fx of 0, 0, then fx is discontinuous at 0, 0. Only when they are equal, you can say it is continuous at 0, 0. First of all, the limit should exist. That is the first thing. And when it exists, it should be equal to the value of the function. Okay. So
Okay.
this is the condition you need to check for continuity.
Do we have any question for this? We can prove and understand better with example.
Like what? I don't get it. What?
The one which just said to check whether this continuous at point 0, 0 or continuous.
I guess we have solved a similar piecewise piecewise function in the limit case. I guess in week 10 beginning we have solved some function.
Yes.
Okay.
Right? Please refer to it.
Okay.
So,
Yeah,
ma'am, for
just
continuous
one.
functions, the partial and the mixed partial functions are going to be same in limits, right? Like the limits will be same.
No, when the limit exists and it is continuous, then only you can say the mixed partial derivatives are equal.
And the partial derivatives as well.
The partial derivatives, how can it be equal?
Like the limit is 0, 0 for both x and y, for both
See,
partial
that
derivatives.
is only for this particular case. There is no such rule that your partial derivatives will be equal at a specific point. No. Please
So they
don't.
can be different and still the function can be continuous.
See, it is this is a different function. This is a different function. Don't compare these two here. The comparison is not about fx and fy. Please
Okay.
forget about this comparison.
Oh, but I'm asking you, like partial derivatives
No,
doesn't
no,
have
no, it
anything
need
to
not
do
be.
with continuity.
No. See, continuous of a specific function is different from the value being equal for different functions at a point. So don't confuse with this. That need not happen. Okay.
Okay. Only mixed partial derivatives.
Yes.
Okay.
Yeah, just one doubt. See,
Yeah.
during this week 10, beginning, we did multiple exercises to verify whether something is function is continuous. By we were using various options like y is equal to mx, y is equal to x square. We were going through 4 or 5 options for the same function. Now with this theorem, if we try and find out that two partial mixed partial derivatives are equal.
But I guess what you're saying is about the directional derivative through some points C, not continuity, right?
No, my thing is this particular theorem says that the mixed partial derivatives will be equal only if the function is continuous. So if we derive these mixed partial derivatives and if they are equal, can we say that the function is continuous?
Not necessarily. The other way need not be true, I guess.
Yeah, because otherwise, see, if to confirm that something is a function is continuous, we were trying different options. See, often one or two values alone were not sufficient. We were using equations like y is equal to mx, you try, y is equal to x square, you try, in addition to our normal cases. So My only doubt is, can we use this theorem, to confirm
I don't
that?
think the converse is true.
Okay, thank you.
Okay, fine. Yeah. So Clairaut's theorem says that this mixed partial derivatives are equal only when the partial derivatives, first partial derivatives are continuous at that specific points. Okay, fine. Now we are considering second order partial derivatives for functions of any n variables. So far we saw only for two variables. Now let us consider functions of any n variable. Now if you are considering n variables, so again the concept is going to be the same. Suppose, let us say in the same terminology I am saying, suppose you are having a function fx1, x2, x3, x4 up to x4 I am writing, yeah?
Excuse me, ma'am. Ma'am, but why is converse not true? Like logically speaking, it should make sense, I think.
I'm not sure why, but I somehow feel that the converse need not be true. If you want a logical explanation, maybe we still have the Sunday session for week 11. We can discuss at that time. I don't have a solid reason here, but I somehow feel that it need not be true. We'll discuss again in week 11, 10, Sunday session of week 11. Okay?
Okay, please, ma'am. Thank you.
Sure.
Yeah, that will be great, because the other methods, sometimes looks like a lottery.
Sure. Definitely we'll discuss again. Yeah.
Okay, thanks, ma'am.
Okay, so for example, you can have functions of 4, 5, any number you can have. Okay, so for example, if you are having x1 square plus x2, x3 plus e power minus 5 x4. Okay, this kind of a function you can have. The concept of the partial derivative second order, it is going to be the exact same thing as before. So now what is fx1 here?
2x1.
2x1. Now what is
2x1.
fx1, x2 here?
0.
0, right? And what is fx3 here?
x2.
x2.
Okay. Now what is fx3, x2?
1.
1.
Okay. So the concept of finding the partial derivative is not going to change. Even though the number of variables keep on going to increase, the concept is still the same. And also the Clairaut's theorem is also going, you have to write it accordingly. For example, if you are having functions of 3 variables, let us say f, y, z. Okay. So the mixed partial derivative, now you are going to have like f, x, z, y, z, zx. These are going to be same. Okay, and fxy, fyx are going to be same.
Ma'am,
Yeah.
just checking Google, like the converse is not true, and they are given like a lot of examples for it also. Like,
Yeah, I also feel that the converse is not true, but I don't know exactly what is the reason why it is not true. Maybe I can check it and we'll discuss again. That was my feeling that the converse is not true.
yeah, they have given examples. They haven't given like a detailed proof or anything. Maybe it's,
Okay, I'll see anyway. And usually the thing is that whenever there is some theorem and the converse is also true, usually it is mentioned along with the theorem. Okay, if it is not there, then it is suspicious. Okay, if the converse is true, then usually they don't give. Then they say if and only if. Okay, fine.
Okay.
I'll look for why it is not true. If possible, we'll discuss with the counter examples also. Okay, fine. Fine. So here you are having now a function of 3 variables. Now what is, I guess this kind of problem we have done earlier. Now what is fx?
Y plus z.
And what is fy?
X plus z.
And what is fz?
X plus y.
And what is fxx?
0.
And what is fyy?
0.
And what is fzz?
0.
Okay. Now what is fxy?
1. fxy.
And what is fxz?
1.
Yeah. And what is fyx?
1.
And
One.
what is fyz?
1.
And what is fzx?
1. 1.
And what is fzy?
1.
1. Right? Pretty simple, right? So same way you can find higher order partial derivatives also. For example, in this function here, whatever function you are having here, so here you are having f x3 x2. Now what is f x3 x2 x2? You are finding, now you are considering this as a function and finding the derivative with respect to x2 now. What is the answer?
0.
0.
0, right? That's all. You are going to consider the second order derivative now as a function to find the third order derivative. That's all. Okay. And here also the Clairaut's theorem will apply accordingly. For example, if you have f x y z, it is going to be same as f x z y, and it is going to be same as f y x z. Okay. Any other possible combinations? F maybe z x y. All these are going to be same.
Yeah.
Okay, provided your fxy, fxz, fyx, all these are continuous. Provided this fxz, fyx, and fzx, all these are continuous. All the second order partial derivatives are continuous. Then you have it for the third derivative, the Clairaut's theorem property. Okay. So this condition you should appropriately use. Okay. Also, you should have here fx, fy, continuity of continuity of fx, fy, fz also are needed. Then only you first of all know fxy is same as fyz, fyx, right? So all these are accordingly needed. Okay. Fine. Let's do some Next, Hessian matrix directly comes. So I wanted to discuss some problem which I told you to remind me for higher order partial derivatives. What was the problem?
E raised to something.
Yeah, it's here. See, for this kind of example, since the concept is going to be repetitive, they may be asking what is the, for example, dou power 10 f of x comma y by dou x power 10, something like this, 10th power. Or generally they can ask dou power m f of x comma y by dou y power m, where m is even or m is odd, something like this. This kind of questions can be asked because it is going to be repetitive. For example, for 10 case, what is your guess? You see, you are having now fx is 3 e power 3x minus y, and fxx is 9 e power 3x minus y. So what will be the 10th derivative with respect to x?
3
power
raised
10.
to 10.
Yeah, 3 raised to the power 10 e power 3x minus y. And what about fyy raised to the power for some even number? Let us take some even number. Then what is the partial derivative with respect to y for the m derivative?
E
power
raised to
3x.
3x
It
minus
is
1.
the same function. If it is odd, then
Minus e raised to 3x minus 1.
okay, you understand what is the question here. So you can be asked any power or any partial derivative, any order partial derivative, if you are having some specific value for your partial derivatives, if you have some repetitive property. Okay, fine. This is what I wanted to tell. Fine. Yeah. So the next concept here is that what are Hessian matrix? Okay. See, why we need this Hessian matrix? What are these Hessian matrices? See, in the case of one dimension, when you know what are the critical points, how do you find whether the critical point is a local maximum or minimum?
With second derivative.
Derivative less
Yes,
than
you
0.
use the second derivative test. So in the second derivative test, you have the second order partial derivative, and you find the second order partial derivative, and you look at the sign of the second order partial derivative at the given point, right? So since here you are having partial derivative, you have several different variables. So here what we are doing is that we are considering a matrix. Okay, and in the next slide, we will see how this matrix is going to contribute to the classification of the critical points. Okay, fine. So what is this Hessian matrix? Let us see. Let us say you are having a function f of x1, x2, xn on a domain D. Okay. Then the Hessian matrix of f It is defined as, you see, now here, for example, let me simply consider the function f of x comma y. Then what should be the Hessian matrix here? fxx, fxy, fyx, and here
FYY.
yy.
FYY.
Okay, fine. So fxx, fxy, fyx, fyy. This is what you are considering. Okay, and then
If we
what
get
about,
3 by 3 then?
yeah?
If we look into 3 by 3 matrix then?
Yeah, that is what I'm going to do next. So now if you are having 3 variables, then what is your HF here?
FXX.
fxx, fxy, fxz, fyx,
FYX, FYY,
fyz,
YY,
fyy, fyz,
YZ,
fzx,
FZX, FZY,
fzy, and then
FZZ.
fzz.
okay, fine. So this is the Hessian matrix with respect to 3 variables. So as you keep on increasing the number of variables, the number of rows and columns are going to increase accordingly. Okay, so here you remember this is your x1, x2. Here it is x1, x2, x3. So as the number of variable increase, you know what to do. Okay, so if you are using the 1, 2, 3 terminology, actually it is very easy to observe that. Suppose you are calling this as a matrix A, then your ij coordinate of your matrix here is nothing but f, xi, xj. Okay, suppose you call this matrix as A, then the ij coordinate of this matrix is fxi, xj. Very simple. Okay, fine. Now, what is f of x comma y equal to x plus y? What is a Hessian matrix for this particular function? We have already computed what are the partial derivatives. So we saw that fxx, fxy,
All 0.
fyy both are 0. And also fxy and
0,
fx
0, 0,
One.
0.
all are 0,
1.
right?
All
So
0,
your
0.
Hessian matrix in this case is the 0 matrix,
0, 0, 0, 0.
right? And for this one, I guess the expression was a little bigger, if I remember. Please go back and look at the expression. I guess I have written it down here. So HF is equal to, now you have fxx, fxy, fyx, and fyy, which is equal to minus y square sine of xy cos xy minus xy sine xy, the same cos xy minus xy sine of xy, and minus x squared sine xy. Since I have already solved these problems, I am not repeating it here. I have already solved the sine xy, right?
Yes, ma'am.
Second order also did I solve?
Yes, ma'am.
Yes, I guess, ma'am. Yes, we did that, I remember.
But one differentiation alone is going
Yeah, I
to
have done
take
it
some
too.
time. But
We done that one.
multiple difference. It is multiple differentiation. In exam, it will take so much time just to differentiate.
No.
See, if it is a simple function like this, it is not going to take much time. But if it is a little complicated like this, yeah, a little more time you need. Anyway, you
Yeah.
are not going to have very difficult things. Maximum 3 variable or very, very rarely 4 variable is going to come. I don't think 4 variable and all is going to come. Even if it is coming, maybe it is going to be a very, very simple function. Okay, so don't worry, it is not going to be that difficult.
Ma'am, by the way, like, what is the use of Hessian matrix?
That is what I told you. It is going to help us for classifying our critical points. We'll see it in the next slide.
Critical points. Okay.
Okay.
Just one doubt about this Hessian matrix. See, if you normally look at a matrix, no, the values relating to a particular variable, it comes in on the column. So when we look at the structure which is given, see the column shows xx, then y. If you go slightly up, where we now a little more, where we have seen that red the 3 matrix. See, it shows xx, then the column yx, and then lower part is zx. So, is there a specific reason for it, or even if we reverse, like in the first column we put all f xx, then f xy, then f xz. Is it going to make a difference?
So you are saying that why this specific order we are considering? That's
Yes,
what you are
yeah, yeah,
asking.
because normally in matrix, if there is a variable x, it's represented in that column rather than on the row.
Of course, there is a specific reason why we are considering this. Because of this specific order, something like a second order derivative, you had this, what is it? Yeah, second derivative test. So similar thing we are going to have next using this Hessian matrix. For that, we need this structure. When we have this structure only, we can have those specific properties there. Okay.
Okay.
Ma'am, I have one doubt. Like, if we take the general form, the x2 should be like outside, right? Like x1 should be outside, right? We are actually derivative taking the derivative of the gradient, right? Whole gradient first line, so that x will be the last term in everything, right? Not the other way around. Like x1, we are taking the derivative with respect to x1 for all the elements. So that will be the outside one, right? Like it should be like f of y is like it should be that way fxx, fyx, fzx. And the second one we are taking with respect to y. So it should be like uh, xy, fyy, fzy. So
Okay, I understand what you're saying. Yes. What you're saying is right. The notation is varying, right? Yeah.
yeah. So it should be like what we wrote, like
The
when you
transpose of
wrote
this
in,
you are saying, right?
it should be the transpose, right?
Yeah. What he's saying is correct. See, what happened here, let me go back to where we have defined the second order partial differential. Yeah. So here you see fxy means first your y is coming and then x is coming. So whenever you are having dou squared f by dou y x, it means what is that you are having? So x and y, the places are interchanged. X and y, the places are interchanged because of this reason. Yeah, thank you for pointing. Really, thank you for the point. This is a really important thing here. I missed it. So here you see, here it is actually fxjxi. That is what he is pointing out, right? Fxjxi. So fxjxi is this ijth entry. Okay, so you are first finding the partial derivative with respect to xj, and then finding the partial derivative of fxj with respect to xi. Yeah, exactly. So the transpose of these matrices. Luckily for these examples here, they are same, so we don't have to worry about it. Otherwise, in general, what he's saying is that here it should be actually fxx, fxy, fxz, and here fyx, fzx, and here fyy and fzx. Sorry, z.
Yeah, that was my doubt as well. Why it is not.
Thank you for pointing. Yeah. Okay, fine. And now if we are writing the values, what are the values for this second order derivatives? Along with the diagonal, it is very easy. What are the diagonal entries here?
0, 0, 0.
0, 0, 0.
Yeah. And what about all other entries?
1.
Yeah.
1.
All other entries are simply 1, 1, 1.
Identity.
Right? Sorry, is this identity matrix?
Yeah.
Yes. Are you sure?
No.
This is not identity matrix. It is
No. This is not
opposite of
identity.
it, right? For identity
Not
matrix, the
identity.
diagonal entries are 1 and all other entries are
All
0.
others are 0.
Okay. Fine. Okay. So now what is the second derivative test? Let us quickly recall. So what do we do for the second derivative test? Let us say, first of all, you have a function d to r be a function of one variable on the domain D. A point A to D is a critical point if either f is not differentiable at A or f dash of A equal to 0. Right? Suppose f is twice differentiable at A, then the second derivative test can be applied to check the nature of the critical points. So how do we check the nature of the critical points? So if the second derivative is positive at the specific point, then we say that it is a local minimum. If it is negative, it is a local maximum. And if it is 0, the test is inconclusive. Now we are going to do a similar thing with Hessian matrix, which is called as Hessian test. Okay, so we are going to classify the critical points of f of x comma y. So first let us look at the case of two variables. Let us consider the function a critical point a tilde. Okay, then see here one important thing is that they are assuming that the first order and second order partial derivatives are continuous. So what happens if this is the case? What happens? If your first
fxy
order,
equal to fyx.
yeah, it does not matter. So this matrix is going to become a symmetric matrix. So what does this guarantee? This guarantees that your fa of a tilde, it is a symmetric matrix. What are symmetric matrices, by the way? The matrix has
Transpose will be same.
yeah. So in that case, you have a symmetric matrix. Okay. So that is why there is an advantage whether you write it in this form or that form. It did not matter. Anyway, it is important that Hessian matrix is actually this. Okay. It is important to note that. But for this Hessian test, we are lucky enough that this condition, this assumption is there. So HF of A tilde is going to be a symmetric matrix. So you don't have to worry about it. Okay. For the Hessian test, don't worry. Okay, then the Hessian test can be applied to check the nature of the critical point. How is that we are going to do? We are going to look at the determinant of this Hessian matrix and also look at the value of the second derivative at the specific point. Okay, so first of all, you have three cases when the determinant is positive. When the determinant is, let's say this is case 1, this is your case 2, and this is your case 3. So in case 1, you are going to have local extrema. Okay. Case 1, when the determinant is positive and also the second derivative is positive, you will have local minima. And in the determinant is positive with the second derivative value is less than 0, you have local maxima. Okay. And the determinant, if it is less than 0, then it is going to be a saddle point. And if it is equal to 0, the test is inconclusive. Okay. Quite certain things to test, but it is quite easy also. Okay, let us see f of x comma y. First, let us find and classify the critical points. Okay, so how do we find the critical points first of all? Can you tell how to find the critical points?
Taking a derivative and equating it.
Exactly. First, find the gradient. So del f of x comma y. What are the gradient functions here?
2x,
2y.
2x comma 2y.
Okay. Now, if 2x comma 2y and if it is equal to 0 comma 0, then what is that you are going to get as the critical point?
X equal to 0 and y equal to 0.
4.
So your critical point here is 0 comma 0, right? So this is the critical point. Now, what is your Hessian matrix? Or better, let us stick to our notation. So let me remember, this is fyx and xy. Okay. So what are these?
2 0
2x. So 2 0
2 0 2 0 2 2 0 0 2.
So HF of 0 0 is also going to be the same matrix. Now what is the determinant of HF of 0 0?
4.
The determinant is 4. Which is positive. Yeah. The determinant is 4, which is positive. And what is fx of 0 comma 0? 2. Again, it is positive. So if it is again positive, then what is the category it falls? So you see, this is positive, this is also positive. So what is the critical point now?
Local
minimum.
So 0 comma 0, it is the local minimum. Local minimum. Okay.
Why? Is there any reason why this is specific to fxx? Why not fyy or fxy or fyx?
I don't know exactly what is the logic behind it. I don't exactly know what is the logic behind it, but usually what happens here is that as the number of variables increases, there is some specific order which is followed.
Maybe symmetry because I mean if we
Hold
take
on.
FIY also it's the same, right?
Hold on, there is someone who is talking something else. Yeah, I guess now they are. Still, I hear some other voice. Who is that?
Manish, can you go on
Please
mute?
turn on mute.
Okay, I'm muted. Okay, fine. So when you see, when you are having the three variable case itself, you are going to take some specific order where the first variable is going to contribute something, second and first and second together going to contribute something. So each variable has some specific role to play when the number of variable is going to increase. So why specifically x6 here? What is the logic behind the theory part? Here, I don't know exactly what is the logic behind. Maybe if you want some reference, I can go through it and let you know. Okay.
Okay, ma'am. No, sure.
Next here, HF. Before that, what are the critical points? Del F. Let's find what is del F for this function. Next function.
Minus 2x minus 2y.
Minus 2x.
Minus 2y.
Minus 2y. So now del F of x comma y equal to 0 comma 0 will give you what are the critical points then?
0, 0.
0, 0.
It is 0 comma 0 again. So now the critical points are again 0 0. Now what is your Hessian matrix?
Minus 2 0
2 0 minus 0 minus 2.
0 minus 2.
And what is the determinant of your Hessian matrix? This
4.
is it is 4, which is positive. And what about your fxx of a tilde?
Minus
Negative.
2.
Minus 2.
Less than
So it
0.
means your 0 comma 0 is a
Local maxima.
local maxima. Right? Okay. What about this case? Now again it is going to have gradient 2x minus 2y.
Minus 2.
So you are going to have the same critical point here as well, which is 0 comma 0.
0.
Now what is your Hessian matrix here?
2 0 0 minus 2.
Okay. Now what is, let's say this
Just one doubt. In this case, the value x and y may not be zero. No? Any
x and y.
you give same value to x and y, it will give zeros.
If we give same value to x and y,
the critical, you will still reach the critical point. No? So there are a lot of critical points, right?
why 2x is equal to 0 minus 2y is equal to 0. Only
It's not
option
2x minus 2y. It's 2x comma minus 2y.
Oh, okay. Sorry. Yeah, apologies.
Okay.
Yeah.
Fine. Okay. So HF of a tilde, what is the determinant?
Minus 4.
Minus 4.
Minus 4. So you don't have to look at the second derivative directly. You can say that a tilde is a saddle point. Okay.
Sorry,
And-
madam, can you please help me with finding the critical point? Yeah.
See, for critical point, first you are finding the gradient. That is fine for you, finding the gradient.
Yeah.
So this is your fx and fy. So this is your derivative with respect to x, derivative with respect to y. And then what we are doing, we are equating this to 0. It means what? 2x comma minus 2y, equating it to 0, 0. So first coordinate match to 0, second coordinate also match to 0. So 2x is equal to 0, minus 2y equal to 0. So this implies x is equal to 0 and this implies y is equal to 0. That's all.
Ma'am, regarding that earlier fxx, just thinking, I'm not sure. Like what we are doing is like we are doing a quadratic approximation, right? Like for this, like unlike the single variable, here we are doing like 2. So then we check like if it's going up or down, right? That's what we are doing, right? If it's like local minima, local maxima. So we do that in respect to the x-axis, right? That's why it will be xx, right? Just Like if we take it in terms of FYY, then we won't get that, like if it's going up or down like the curve. So maybe that's why we are doing it with respect to fxx, right?
Okay, maybe.
I'm still not sure. Okay, thank you for saying, but anyway, I will look into it and we'll discuss again, because this week 11, I will tell you, it is a very small. The topics we can cover in a very short period. So today itself, most of the topics we will be covering. So whatever doubts you have, no issues. Sunday we will have plenty of time for discussion. Okay.
Okay. Thank
Okay.
In which case, this critical point cannot be 0, 0 then?
Here 0, 0 is a critical point only.
And I'm saying, and what are the certain cases whereby the critical point cannot be 0, 0?
There is no specific rule like what are the critical points, depends completely on the function. Okay, it completely depends on the function. For example, suppose you have plus 2xy here, then the critical points are going to change accordingly. Okay, so it completely depends on your function. There is no specific rule like what are the critical points can be. Okay?
Is it possible that critical points could be more than one?
Of course, there can be several critical points.
Okay.
Okay, we will see examples. Next examples we will see.
Sure.
Okay. Fine. See, even in one variable case, you are having several critical points. So you can expect the same here as well, right? Okay. So f of x comma y equal to x power 4 plus y power 4. Now, what is the gradient function?
4x cube comma 4y cube.
4x cube. Yeah.
Okay. Now, what is the critical point? Again, we are equating it to 0. So 4x cube equal to 0. 4y cube equal to 0 will give you x equal to 0, y equal to 0. So your critical point is again 0, comma. Okay. Now what is your Hessian matrix?
12x square.
12
X square.
12x square and then 0,
0, yeah.
0.
12y square.
12y square.
Okay. And now Hessian matrix at the point 0, comma 0 becomes the
0, 0,
0
0.
matrix.
so the determinant is also
0.
so if the determinant is 0, what about the test?
Inconclusive.
Yeah.
Conclusive.
So the test is inconclusive. We cannot conclude anything from this. Okay, fine. Let us look at the next example. So whatever you were asking, like there can be more than one critical point. Here is the example. So now let us look at what is the gradient function. What is the whoever asked how to find the critical point, please listen carefully. Now what is the gradient function here?
2x plus 6y
2x plus 6y plus 8y.
plus
Plus
2
2 comma
6x
6x
plus 8y
8y minus 4.
Okay. Now to find the critical points, you have to equate this to 0. It means 2x plus 6y plus 2 equal to 0. So I can write it as equal to minus 2. Right? And also 6x plus 8y minus 4 equal to 0. So I am bringing the minus 4 to the other side. So now you have to solve the system of linear equation. So let us write this as 6x plus, I'm multiplying the whole
18y.
equation by 3. So I'm getting this. So here 6x plus 8y equal to 4. So if I'm subtracting, then what you are getting? 10y equal to
minus 10.
Minus 10. So what is your y value?
Minus 1.
Minus 1.
So if you're substituting it back here, you are getting 2x minus 6 is equal to minus 2. So 2x is equal to
Minus
8.
is equal to
2.
So here, what is the critical point here?
2 comma
2
minus 1.
comma minus 1.
Okay. So it need not be 0 comma 0 all the time. And also finding the critical point, sometimes you have to solve system of linear equation like this. And sometimes it need not be system of linear equation. You have to solve some polynomial equations also. Okay. So we will see one by one. Okay. So now you have what is the critical point. Now let us look at what is the Hessian matrix. What is your Hessian matrix now?
2,
What is the derivative of this with respect to x?
2.
What is
This
the
is
derivative of this with respect to y?
8.
8.
What is the derivative of this with respect to
Y.
Double
y?
X.
6.
Sorry, I told the wrong one here. So here for this derivative of this with respect to x, which is
X.
6.
and derivative of this with respect to y,
6.
and derivative of this with
8.
respect to y, 8. Okay. Now
16
what?
minus
16 minus 12. Oh, 6 minus 6.
36.
Let us
16
16.
minus 36 minus 20.
20 minus 20.
So which is less
Yes.
than
Lesser
2.
than 0.
So your 8 tilde, which is 2 comma minus 1, it is a
Saddle.
Saddle.
Saddle point.
7 points.
okay. Fine. All right. What is for now for this function? Again, please listen carefully. What is the gradient function for this?
Y minus
Y
y
minus 3x square.
yeah.
Y
Minus
minus
3x square.
X
square, and then
Comma
x
x
minus 2y.
2y.
all right. Now we are going to equate this to 0. So what is that? You will get y is equal to 3x square and x is equal to 2y. Okay. So now how do you solve this? Can you give any idea how to solve this?
2y equal to 6x square. 6x square equal to x.
Put y is equals to x by.
Substitution method. Yes, ma'am.
Yeah.
Yeah, any way you can do. There are two ways. Either you substitute this here or
Correct.
this you can substitute here. In either way you can do. Okay. So suppose let us say you are substituting your
X, y is equals to x by 2.
yeah. Then this is equal to 3 into 4y square 12y square. So this equation now reduces to y square minus 12y square minus y equal to 0. So y times of 12y minus 1 equal to 0. So now from this what are you getting?
Y equal to 0, 1 by 12. Or y equal to
Okay. So if y is equal to 0, what is the value of x?
0.
And if y is equal to 1 by 2, then what is the value of x?
Ma'am, 1 by 12.
Sorry. 1 by 12, then what is the value of x?
1 by 6.
1 by 6. Okay. Are you going to get the same similar answer if you are going to substitute in place of y, if you substitute 3x squared, are you going to get the same?
Yeah.
Okay. So you can do either way. So here you see you get 6x squared. So you have 6x squared minus x is equal to 0. So x times of 6x minus 1 equal to 0, which is going to give you x is equal to 0 or 1 by 6. The same. Again, when you substitute it, you will get the same y values. So either way you can do. It does not matter which one you are using. Either way you can solve these things. Okay. Now how many critical points you are having?
2.
What are the critical points?
2 sets.
0, 0 and 1 by 6,
No,
1 by
no,
12.
yeah, 4.
Only 0, 0 and
1 by 6, 1 by 12.
only these two are the critical points, not 4. Okay. So now what is the Hessian matrix in this case? So derivative of the first component with respect to x is
Minus 6x.
and derivative of second component with respect to x
1.
1 and derivative of first with respect to y
1.
and derivative of this with respect to y.
Minus 2.
Okay. So now hf at 0, 0 is
0, 1, 1 minus 2.
and the determinant is
4 greater than 0.
And 0, 0, right? At point 0, 0 minus 6x, that would be 0, right?
11, ma'am.
which one?
The first value.
Oh, sorry.
First one will be 0.
Yeah. So
The determinant is
determinant of
-1.
yeah
Minus 1.
is -1. If it is -1, then what can you say about 0, 0?
Saddle point.
So this is less than 0, so this is a saddle point. Okay. Now what about HF of 1 by 6, 1 by 12?
-1, 1, 1, -2.
So the determinant of HF of 1 by 6, 1 by 12 is
1.
1 is the determinant.
1.
okay. And what is your FXX of 1 by 6, 1 by 12?
-1. Less
It
than
is less than
Minus
0.
0.
So
Maybe.
1
Local
by 6,
maximum.
1 by 12 is a
Local maximum.
maximum.
Ma'am, I have just a question.
yeah.
Like the point is a critical like a critical point is a point of local extrema only if the determinant is positive,
Yes.
and if it's negative then it is by default it's a saddle point.
Exactly.
Okay, ma'am, that's what I want.
Okay.
And if it's 0 then it's inconclusive.
Yeah.
Okay.
Okay. So this function already we have done. So, but here again you see that what are the critical points? It is a little not straightforward, we can say. So let us do this problem also. So what is your del f of x comma y? We have already done this. Y
Cos of xy.
Y x cos xy.
Okay. So now how do you find the critical points? So you put y cos of xy equal to 0, right? And also you put x cos xy equal to 0, right? So there are two parts for this function. So the product of y into the cos of xy. So either you have y is equal to 0 or
Cos xy equal to
xy is
0.
0. Okay. So if cos xy is 0, this term is also becoming 0. So either you have x equal to 0, y equal to 0, or you have cos xy is equal to 0. Right? You cannot have x equal to 0 and cos xy equal to 0. Why is that so? You cannot have both this together. Why? Can you tell?
Then the other one will be 1 cos.
Yeah, cos 0 will become
1.
1. Okay, so either this case or this case. Okay, so in this case, we cannot combine both these conditions. You all understand why we cannot combine?
Yes,
Even
ma'am.
in the case if y equal to 0,
Then also you cannot combine both this together, cannot happen. Either this or this. If y is 0 or x is 0, your cos 0 will become 1.
okay. So
Okay,
then
both of
one
this
point
together
is
cannot
confirmed.
happen.
X0 and Y0 that we can combine. That point is
Yeah, this
confirmed,
part
right?
we can combine, yeah.
Okay.
Okay, so now can you tell what are the critical points?
0, 0.
0, 0.
And
Cos of xy 0.
Cos of xy.
cos of xy 0. How can you take that as a critical point?
Xy equal to 2 and plus 1 pi by 2.
So here you don't know explicitly what are the values for which your cos xy is equal to 0. Okay. So any xy for which your cos y becomes 0, all those x comma y are now a set of critical points. Okay. There are several critical points in this case. Someone was asking how many critical points. So you see for any xy where cos xy is equal to 0. So for example, if x is equal to, I don't know, some product where you get the product to be pi by 2, then you know that it is 0, right? So like this, there are several possibles for xy where cos xy is, it is equal to 0. So here the critical points are all the points 0, 0 and the set of all x, y such that cos xy is equal to 0. So all these are critical points. Okay. Now, explicitly, we don't have to write because there are so many points. Okay, now one thing you have to remember. Okay, let us do the next step and then we will come to this. Yeah. What is the question?
Yeah, that's the same thing again. Y equal to 0 and cos of xy equal to 0. Why we cannot take?
Okay.
Y into
because-
cos of x of y will be
okay,
0,
let
right?
us say y is 0 and cos xy is 0. Okay. Now, since y is 0, your cos xy is nothing but cos
1, 1. Okay, cos 0, 1.
which is
Okay.
not the case here. So we cannot combine this together,
No,
right?
anyway, the full equation is 0, right? Y into cos xy is 0. That is matching, right?
See, that is matching, that is fine. I'm not talking about this. Here, this together cannot happen, I'm saying. This and this, how can they happen together? We are talking about this and this happening together.
No, it
At the same
can
time,
happen, right?
when the
Are you
y,
saying if it happens, the equation will not satisfy?
That is not, that is what I'm not talking about. The equation will not satisfy. I'm saying this itself, irrespective of this equation, this together cannot happen.
even if that happens, madam, then what will happen is you would not be able to determine what is the value of x because y is affecting the cos
It's
value.
not about we cannot find x. See, when y is 0 or x is 0, your cos value, see, you don't have a solution for this system of equation. There is no x comma y which satisfy both this condition. That is what I'm saying. Okay, there is no x comma y which satisfy both the condition, because if you are having an x comma y where y, suppose x comma 0, for this point, you know already y is 0, can, for this point, can xy cos xy be equal to 0? No, right?
ma'am. No, ma'am.
So there is
Be
no
one
x
again.
comma y for which both the condition can happen. So such a point does not exist, I'm saying. Okay,
Okay.
is it clear or not?
Oh,
Yes, ma'am.
see, the y cos xy equal to 0, that is the equation. It could be either y equal to 0 or cos of xy equal to 0.
Okay,
And
now
it's a or
okay.
condition. Why are we considering y equal to 0 and cos of xy equal to 0?
That is what I'm saying.
It's a
We
or
cannot consider. We cannot consider. That is what I'm saying. It's or only. Sometimes it is possible. See, for example, here what did we do? Here what did we do? We considered y equal to 0 or y is equal to 1 by 12. Both these cases we consider corresponding to this y equal to 0, x is
Yeah.
equal to 0 we find, and y is equal to 1 by 2, x is equal to 1 by 6 we consider. Here only y values are coming, but here it is not explicitly y. It is some function cos x y equal to 0. I'm saying this two together I cannot say. Okay, cos xy is 0. Suppose cos xy is given as, suppose let us say 1. Then I can consider all the cases where y is also 0. Then that case can be considered separately. You understand? Okay.
Okay.
Fine. Okay, I will write in statement what I wanted to say. There is no x comma y such that y equal to 0 and cos of xy equal to 0. That is why I am not combining this and this. Okay, fine. Okay, now what is your Hessian matrix? The derivative of this with respect to x.
With
What is
respect to
that?
x.
Y square cos x square.
Y square.
Yeah, y square.
Y
Or
square.
cos sin
Minus
y square
Sin
sin
x.
xy.
xy. Okay. And what about the derivative of this with respect to x?
With respect to x.
P.
Xy minus xy sin xy plus
Cos of xy.
The
cos
same
of
here
xy
also.
minus y sin xy plus cos of xy
And then here you will have
minus x square sin of xy.
okay, fine.
Yes.
So now we have obtained up to this. Now what we have to look at is what is hf of 0, 0. First let us consider the point 0, 0. What is this matrix? This will
Zero
become
matrix.
this will become 1. This will also become 1. And this will become
0.
Now what is the determinant of this matrix?
Minus
1. Minus minus 1.
Okay, determinant is minus 1. So what can you say about the point 0, 0?
Saddle
Saddle
point.
Saddle.
Saddle
These are
point.
saddle points.
Okay, 0, 0 is a saddle point. All right.
Saddle point.
Now, what about the next case, the set of x comma y for which you are cos xy is 0? Okay, now if cos xy is 0, what can you say about sin xy? Because what happens at those points we have to see. Now, what can you say about sin xy value?
Plus or minus 1.
Yeah. If
1.
cos xy is 0, you can compare it with your graph. This is basic trigonometry property. Cos xy is 0 if and only the corresponding sin xy value is
Minus 1 or
plus
1.
or minus 1. Okay.
1.
So with this condition, now let us consider the set S. Okay. Let us say, for example, this is set. Okay. Let x comma y be any point from your set S. Now what happens to your HF of x comma y? What happens to your sin x comma y value?
Plus or minus y square.
Plus or minus?
Y square.
Plus or minus y square. Okay. And this one, this cos xy is 0. And here you will have?
Again plus or minus xy.
Yeah. And then here, I guess we have to be careful about the plus or minus.
Minus
Okay, let us write it separately. Okay. So first let us consider the case when sine of xy is equal to 1. Okay. Let us write this separately. That is better. So when sine xy is equal to 1, this is minus.
Minus y.
This is minus again. And
Minus
here
xy.
it is.
Minus xy.
And here?
Minus x square.
Minus xy. Okay. Now, what happens to the determinant of your HF of x comma y?
0.
Square y square. Yeah.
Y square minus x square y.
0.
Which is
0.
So if this is 0, then what can we say about that points?
Inconclusive.
Inconclusive.
Inconclusive, right? Okay, this is in the case of sine xy equal to 1. Now, what about the case when sine xy is equal to minus 1?
Same. It's the same.
So in that case, you have
Yeah. Y square xy.
xy.
X square.
Yeah, again 0.
Again 0.
Again determinant of HF of x comma y is 0. So in either case,
0.
for any x comma y in S, all of them, the test is inconclusive. Okay, fine. So after this, I hope everything is clear. So next we have to look at the same Hessian test for functions of 3 variables. Okay, so functions of 3 variables, let f of x comma y comma z be a function defined on a domain D in R3 and a tilde be a critical point. Now Hessian test is a little involved. You have 3 things to see. So you first look at what is fxx of a tilde, whether it is positive or negative. Okay, and then you also look at the determinant of, first of all, what is the matrix here? Let us write here HF is equal to fxx, fyx, fzx, fxy, fyy, and fzy, and fxz, fyz, and fzz. Okay, so now this is the matrix. So now here you see that. So first we are looking at the first component, fxx of a tilde. And what is this part here? What is this part here? This part
The determinant of the first four. I mean, yeah.
Determinant of this part, right? What is the determinant of this part?
Fx square minus fx square fy square.
Fxx fyy minus fxy the whole square.
Fyx.
Okay, so here you see that here square, because both of them are same, they are symmetric matrix, because we are considering the first and second order partial derivatives are continuous. So by Clairaut's theorem we know that it is a symmetric matrix. So fxx fyy minus f squared xy. Okay, So the determinant of this matrix, and then we are considering the determinant of the whole matrix. So 3 steps we are considering. Okay, so first this should be positive, this is positive, and all of them are positive. If all of them are positive, then you know that you are going to get a local minimum. And the second case is that you are going to have a negative first, and then a positive, and then a negative, then local maximum. In all other cases where the determinant is non-zero, okay, so it means your case 1 and case 2 does not occur, then you have A tilde as a saddle point. Okay, it means what? Suppose, so let us say your fxx of A tilde, here this is determinant of, I don't know, maybe I'll write this itself, your fxx fyy minus fxy square at A tilde, and then here determinant of hf of A tilde. Okay, so you have 3 things to compare. Now first, if you have all of them are positive, then what is going to happen?
Local minimum.
Local minimum. Okay, and now first one is negative, second is positive, third is, then it is a
Maximum.
Local maximum.
Okay, and then when you know that this term here is non-zero, and whatever other case, whatever is the case,
Saddle points.
other cases, not this two, any other cases, if you have, then all those points are saddle points.
Saddle points.
Okay, and when this determinant is equal to 0, then it is this inconclusive.
So first we'll be looking at the total determinant, is it, ma'am?
Yeah, first thing you have to look at is the determinant of this matrix. That is the first thing you have to look. Okay, you have to first look at this, then this, then this. Okay, fine. Okay, so if you see that you find the determinant is non-zero, and then this is negative, this cannot be negative. That is the case we are seeing. This
Maybe that one we can first check, right? If it is positive or negative.
See, if it is negative and suppose it is 0, okay, then you have to see whether it is anyway you have to find the determinant is 0 or non-zero. This is anyway you have to find, right?
Okay.
Okay. Okay. So now, first thing, what is the first step here? For first of all, you have to find what are the critical points. What are the critical points for this function? What is the gradient function here?
0, 0, 0. 2x, 2y, 2z.
So your critical point is 0, 0, 0. This is your A tilde. Okay. Now what is your Hessian matrix?
2, 0, 0. Sorry.
All are 0 only? No, right? What is fxx?
2, man. 2, 0, 0. 0, 2, 0.
0, 2, 0, 0, 0, 2.
So what is the determinant of hf of A tilde?
8.
8.
Which is positive. Okay. So now let us look at this smaller matrix here.
4.
What about the determinant of this matrix?
4.
4.
Positive.
So you have fxx fyy minus fxy square is equal to 4. And that is also positive. And what is fxs of A tilde?
2.
Positive.
Which is also positive. So
So
local
what
minimum.
is the case you are obtaining here?
Local minimum.
Local minimum.
Okay. Now what about this function here?
It looks like the same, right? Minus 2, minus 2, minus 2 will come.
So the critical point is again 0, 0. Okay. Now what is the Hessian matrix?
Minus 2,
Minus 2, 0, 0.
Now what is of your Hessian matrix at this point A tilde?
Minus 8.
Minus 8.
Now, what about the determinant of this part here?
Plus 4. Plus 4.
Plus 4.
Just positive. And the determinant of this part here,
Minus
sorry,
2.
the value of
Negative.
this part here.
Minus 2.
Minus
Negative.
Negative.
So minus
Local
plus
maximum.
minus.
Negative, positive,
So which
negative.
case is this?
Local
Local
maximum.
maximum.
Local maximum. So this point is a local maximum. All right. Okay. Now what about this gradient function here?
2x minus 2y plus 2z.
Okay. So again, the critical point is
0,
0,
0.
0.
0, 0.
All 0.
So what is the Hessian matrix in this case?
2,
2 minus 2.
2, 2, 0, 0, 0, 0, 0.
Okay. What is the determinant of HF of 8 tilde?
Is minus 8.
Minus 8.
Minus
And
8.
what is FXX FYY? Minus
Minus
FXY
4.
square.
Minus 4.
So this is negative, this is negative. So if this,
Saddle point.
yeah. So you see now this has become a saddle point. Okay. When this is negative, you don't have to check for the next one. Directly you can write it is a saddle point. Okay. Now what is del f of x, y, z? 4x cube, 4y cube, 4z power 4. Now what is the answer?
4z cube.
A tilde is
0, 0, 0.
0, 0, 0. So here
12x square.
0.
Y
0,
square. All z square.
0.
0.
so all the
Isn't
other
it
things
0
are
right now?
0. Right? So now
Yeah.
at 0, comma 0, what is the determinant of
Everything will
HF
become
of
0.
0.
0. So you
0.
see, for this, the test is inconclusive.
Inconclusive.
Okay? Fine. Now look at this problem. What about the gradient function for this?
Y plus
Y.
z.
Plus
Y.
that. Y plus.
Okay? So now what are the critical points? So y plus z equal to 0, x plus z equal to 0, y plus x equal to 0. So you have to solve this system of linear equation. Now from this you know that your z is equal to minus y. And from this you know that your z is equal to minus x. And here you know that your x is equal to minus y. So from this two you know that your x is equal to y. Right? Now combining this two, what you will
0.
get?
2.
X equal to y, x is equal to minus y. So it means what?
X equal to 0.
X and y both are 0.
Yeah.
Right? So if x and y are 0, then what about z?
0.
So again, the critical point is,
0, 0, 0.
is this clear? What we have done here, is this clear? Okay.
Yes, ma'am.
Okay. Now, what is your Hessian matrix?
0,
What is your
0,
Hessian matrix? 0,
0,
1,
1,
1,
1,
1, 0, 1,
1,
1, 1,
1, 0.
right? What is the determinant of this matrix? Minus 1 times of 1, minus 1, and then plus 1 time of
1.
1. So it is 1 plus 1, 2.
2.
Did I do the calculation correctly?
Yes.
So the answer is 2, which is positive.
Yeah.
Now what about the determinant of this part here?
0. Sorry, minus 1.
So it is minus 1. So negative. And then here, what is the value here? Determinant of, fxx of this a tilde It is 0. So the test is
Saddle point, right?
yeah, it is a saddle point. It is a saddle point. Okay, fine. One last problem shall we do now?
Yes, ma'am.
This is the last problem for today's session.
Yes.
Fine. It is a bit lengthy. Okay. So here you have, I guess it is quite lengthy. You have like 5 critical points and 5 Hessian matrices to compute. We have, apart from, there is only one more topic left for the next session, which is the derivatives. So maybe we can do this in the next session also, because other than that, there is no other topic to cover in the next session.
No problem.
Okay.
Okay.
So we will do this in the next session. Those who want, definitely you can do this yourself also. It's not a difficult one, but anyway, there are 5 critical points for this function.
It's gonna be this long, I guess.
Sorry?
It's gonna be long, but
Yeah,
I guess.
Yeah. Okay, so the topic so far we have covered today. So what we have seen how to compute second order partial derivative, higher order partial derivative for 2 variables and for n variables also. And we have seen that Clairaut's theorem for mixed partial derivative is applicable when the underlying partial derivatives are continuous at the given point. Okay. And then we saw that we can use Hessian, what is a Hessian matrix and how to use it for classifying the critical points. So these are the topics we have covered today. So I hope everything is clear for everyone, right?
Yes, ma'am.
Yes.
Very well. Yeah.
Okay then.
Yeah. So
Ma'am.
thanks. Yeah. Thanks,
Thank you,
and
ma'am.
good night.
Thank you, ma'am.
Hello, ma'am.
Thank you so much.
I have a doubt, ma'am. What is hyperplane?
What is a hyperplane? Okay.
Yes, ma'am.
So first of all, what is a plane?